start from a larger perspective and then move to a more narrow perspective of bowel endometriosis. And just last week, the New York Times talked about one particular individual whose name was Joseph Coates. He's 37 years old and he has a rare blood disorder called POEMS. He had received multiple treatments and they had finally offered him only hospice care. So he and his partner reached out to a doctor at UPenn who recommended atypical use of drug repurposing, which included chemotherapy treatments and immunologic and other treatments. And within a week, he improved his symptoms, and now he's in remission. Similarly, I'll talk a little bit more about Marina Sirota's lab, who does computational computer drug repurposing. AI enables personalized medicine through digital twins, virtual patient lab replicas built from genomic imaging and physiologic data. A digital twin is essentially a representation of a physical object or system. In healthcare, this translates to a patient's virtual counterpart, creating data from various sources, including imaging, genomics, clinical history, etc. And this is currently being used in cardiology as well as many other conditions. To illustrate the power of collaboration of AI-driven healthcare, let's look at the work of Dr. Dossi in his lab at Georgia Tech, which is just right around the corner. He and his team had looked at intricate mechanisms of cardiac valves using advanced computational modeling to simulate blood flow, turbulence, and heart valves. This complex work led to a collaboration with industry, and together they developed predictive modeling software that provides cardiologists with personalized risk assessments for valve replacements. This has been used across the country at different academic centers to be able to estimate the potential of success for heart valves and to determine perhaps if someone isn't getting the appropriate care and that an open heart surgery or something otherwise might be more beneficial for that person. AI, particularly machine learning and deep learning, can analyze medical images with incredible precision. Imagine an algorithm trained on thousands of ultrasound and MRI scans, capable of identifying patterns that are invisible to the human eye. This schematic here refers to lung nodules, but the process of machine learning is the same. For example, in a study published in Radiology, they demonstrated that we could achieve a sensitivity of over 90% in detecting deep infiltrative endometriosis from MRI scans, surpassing the performance of experienced radiologists in some cases. This could lead to earlier and more accurate diagnosis, allowing for timely intervention. Now, endometriosis, as you all know, is a condition where the endometrial glands are outside of the uterus and can affect pelvic organs, including fallopian tubes, bowel, bladder, and beyond. It affects approximately 10% of women globally, and there's a huge delay to diagnosis, as we all know, and an incredible cost to our patients. When endometriosis infiltrates the bowel, it becomes particularly complex, causing severe pain, bowel dysfunction, and a profound impact on the quality of life of our patients. Diagnosing and managing bowel endometriosis often requires a multidisciplinary approach with gynecologists, colorectal surgeons, and radiologists. Accurate diagnosis is challenging, particularly preoperatively. There are many studies that review the detection of endometriosis, and the sensitivity and specificity can range from 67 to 91%. Several variables can affect this, including protocols of the quality of the equipment, the expertise of the radiologists. And this is where AI can come in. The combination of AI techniques in conjunction with the expertise of radiologists can increase the sensitivity of 90% for DIE detection, improving diagnostic accuracy and reducing delays. It can standardize MRI interpretation and integrate diverse data. And then on the back end for AI, when we think about surgery, and I was really excited to hear the previous talk about looking at surgical case insight. This also can be done with robotics, where they've collected data of specific components of a surgery, And they can divide it up into those specific components, which makes it easier to review video studies or review a video case with other people. This can be used either for the person themselves, for teaching with residents, to review specific parts of a case, which can be easily divided up and pulled up on the system, and then could even be done remotely. Additionally, from those specific components, there are objective performance indicators where you can look at very specific points, for example, how many clicks, how much the surgeon zooms in or zooms out, the amount of force that they use on particular instruments, and then that can be pulled up and compared to either different cases of that same surgeon. They can look back on those specific video components of the case to see why one case took particularly longer than another, or what was the complexity of that case. It can also be compared to other surgeons and kind of globally across different surgeons' timing for each of those specific components. Moving on to drug repurposing. Researchers from Marina Sirota's lab used AI to compare the gene activity of endometriosis to how different existing drugs affect gene activity. They wanted to find drugs that could reverse the harmful gene activity seen in endometriosis. And they looked at many different genes, over 3,000 unique genes differentially expressed by at least one of six endometriosis signatures, and only 308 or 10% were in common. However, 221 out of 299 drugs that were identified were shared, so that's 73%, so a high overlap. Even though the gene activity varied a lot between different types of endometriosis, the computer program identified a number of drugs that might be helpful across the variations. One in particular was phenoprofen, which is a type of NSAID. It's not as commonly prescribed as, for example, ibuprofen. And what they did is they did animal testing to use phenoprofen in an established rat model for endometriosis, and found that phenoprofen successfully alleviated endometriosis-associated vaginal hyperalgesia, which is a surrogate marker for endometriosis-related pain. These findings demonstrated phenoprofen as a potential therapeutic with further testing. Of course, there are challenges. AI algorithms are only as good as the data that they are trained on. We need large, high-quality data sets to ensure accuracy and reliability. This means diverse data from various populations to prevent bias. For example, if an AI algorithm is trained primarily on data from a homogeneous population without racial diversity, it may not perform as well in detecting endometriosis in patients of other ethnicities. This is well documented in AI, where biased training data can lead to disparities in performance. Much like what I observed when I visited the Dossi lab at Georgia Tech, each element of AI in bowel endometriosis is key. Advances in machine learning and AI, case insights for surgical management of bowel endometriosis, and drug repurposing can lead to precision endometriosis care that can provide patients with their treatment options for specific conditions, or the depth of endometriosis. Collaboration is crucial. We must unite researchers, clinicians, patients, and industry to advance AI in endometriosis care. And this is where I believe we're headed with the treatment of bowel endometriosis. It takes a village, and I'm so grateful for all of the collaborators for this